A very good evening to one and all. In this video, we'll see how all the fundamental signals are related with each other. I will derive all the fundamental signals from a one-sided exponential pulse. So let us see this one-sided exponential pulse is defined like this. This is given as x of t equal to e power minus at for t greater than equal to 0. So at t equal to 0, this becomes 1, and as t is going to increase, the pulse is going to decay exponentially. This kind of the pulse is known as one-sided exponential decay pulse. Now if I am going to replace this t by minus t, I mean to say, once you put one mirror on this y-axis, you will get this kind of the signal. This is e power 8t. Just you replace t by minus t. Let this is equation number 1 and this is equation number 2. If I am adding these two, 1 and 2, I will get a pulse like this. This is e power minus at for t greater than equal to 0 and equal to e power at for t less than 0. So this pulse is defined as x of t equal to e power at for t less than 0 equal to e power minus at for t greater than equal to 0. And in a very generalized form, I can write this one as x of t equal to e power minus a mod of t from minus infinity to plus infinity. This kind of the pulse is known as double-sided exponential pulse. So this is called the double-sided exponential pulse. This is your x of minus t. Now you apply the odd property of the signals. Put one mirror here. You will get the image of second signals in this way. This become e power at become minus e power at. This is minus of x of minus t. Let us see, this is equation number 3. If you add 1 and 3, you will get a pulse like this. This is e power minus at for t greater than 0 equal to minus e power at for t less than 0. Right? This a is the constant term. If I am going to put a as 0, I will get e power 0 become plus 1. E power 0, 1 and minus here, so this is minus 1. This is plus 1 and this is minus 1. So this function is known as signum function, and this is given as 1 for t greater than 0, equal to 0 at t equal to 0, and equal to -1 for t less than 0. So signum function can be defined as 1 for t greater than 0, equal to 0 at t equal to 0, and -1 at t for t less than 0. If I am going to add 1 in this pulse, this becomes 1 plus signum of t. So -1 plus 1 becomes 0. So for t less than 0, this is 0. 1 plus 1 become 2, and now you divide this by 2. So -1 plus 1 is 0, 0 by 2, 0. At t equal to 0, signum of t is 0, so this becomes 1 by 2. And for t greater than 0, signum of t is 1, so 1 plus 1 by 2 becomes 1. This is known as unit step pulse. So unit step pulse is defined as 1 for t greater than 0, equal to 1 by 2 at t equal to 0, and 0 for t less than 0, right? So we have derived from one-sided exponential pulse, we derived the double-sided exponential pulse. Then from this one-sided exponential pulse, we derive the signum function, and from the signum function, we derive the unit step pulse. Now you shift this pulse left side by tau by 2. So you get a u of, you shift this unit step left side by tau by 2. So this is minus tau by 2. Initially u of t was starting from t greater than equal to 0. Now this pulse is starting from minus tau by 2. So this is 1 for t greater than minus tau by 2, and this is given by u of t plus tau by 2. Now you strip this one right by minus tau by tau by 2. So you get a pulse like this. So this is tau by 2. So this is known as u of t minus tau by 2. U of t minus tau by 2 means this is 1 for t greater than tau by 2. U of t plus tau by 2 means this is 1 from minus tau for t greater than minus tau by 2. So u of t plus tau by 2 equal to 1 for t greater than minus tau by 2, and this equal to 0 for t less than minus tau by 2. And now you subtract this signals from this one, that is u of t plus tau by 2 minus of u of t minus tau by 2. So you get a pulse like this. For t less than minus tau by 2, this is 0, and this is also 0. So minus tau by 2, this is 0. From minus tau by 2, this is 1, while this is 0 till tau by 2. So 1 minus 0. This is 1, this is minus 0. 1 minus 0, this is 1. For t greater than tau by 2, this also 1, this also 1. So this is 1, this is also 1, 1 minus 1, 0. This pulse is known as rectangular pulse, and this is defined as a rat t upon tau, where this tau defines the duration of the pulse. This A is nothing but the amplitude, and this t defines that signal's rectangular pulse is given in the time domain, right? So in this way we can define this rectangular pulse from the unit step pulse just by shifting the u of t from minus tau by 2 to plus tau by 2, right? And if I am going to integrate this u of t, so integration of u of t 0 to t is nothing but since u of t equal to 1 for t greater than 0, so this is 1 dt 0 to t, and this becomes t, right? So this pulse t equal to 0 means 0, t equal to 1 means 1, t equal to 2 means 2, you will get a straight line. This one is known as ramp r of t. So this is the way how we can derive all the fundamental signals from one-sided exponential pulse. In coming classes also we'll see how we can generate various complex signals by using these fundamental signals. So thank you for today's